Now, what is the correlation between time and frequency domain specifications? So, in this correlation, we can compare the peak overshoot and the resonant peak. Majorly, we can compare a peak overshoot, which is in time domain, and resonant peak in the frequency domain. Let us look at what are the formulas available. We know that both depends on only damping ratio. So, what is the formula of percentage MP? E power minus pi zeta by under root 1 minus zeta square. Whereas MR is 1 over 2 zeta under root 1 minus zeta square. So, both depends on the factor, that is damping ratio. And another important is your peak overshoot is inversely proportional to damping ratio. So, your percentage MP is proportional to 1 divided by zeta. Similarly, your MR is also inversely proportional to zeta. Both are inversely proportional to zeta. As zeta is increasing and these two values decreases, zeta decreasing, those two values increases. For example, if you take zeta is 0. So, when zeta is 0, percentage MP is going to be 100%, whereas peak response, that is your resonant peak, is going to be infinity. When you increase the zeta value from 0 to let us say 0.707, so in between 0 and 0.707, your percentage MP decreases and MR also decreases. But when you compare these two, MR decreases fastly than percentage MP. So, percentage MP slightly decreases, MR decreases very fastly. When zeta is exactly 0.707, your percentage MP drops again down, whereas MR is going to be unity. So, that is the limiting value for MR. When you increase the zeta value beyond 0.707, still there exists percentage MP which is going nearer to the 0, where MR does not exist. So, which means when percentage MP is valid for all the values of zeta from 0 to 1, whereas your MR is valid for zeta value 0 to 0.707. Then when you look at the graph, so the graph here you can take percentage MP and this is zeta values. The other graph we have MR and zeta values. So when zeta is 0 and this is 100%, because peak overshoot is always expressed in terms of percentage, therefore 100% when zeta is 0. Whereas here when it is 0, it is infinity, is coming from the infinity. So both are exponentially decreasing functions almost. But when you closely observe exactly at 0.4 zeta, then we have 25% here, and here 0.4 we have 1.04. So from this onwards, and both look same, both behave similarly, but percentage MP is available till the value zeta is up to 1, whereas here the MR goes to 1 when the zeta is 0.707. Therefore, when you look at this, we have the hashed portion in this graph and in this graph. So, this is the correlation exists between your percentage MP and MR. So, the corresponding zeta value is between 0.4 and 0.707. When zeta is operating 0.4 and 0.707, so we can easily correlate percentage MP and MR. So, we know that zeta, the optimum value of zeta is around 0.6 and 0.7. So, when you operate in that range, the most of the system designs satisfies, therefore, we can also satisfy both these two conditions. In control system, there are majorly 3 types of transfer functions. So, those 3 types of transfer functions are minimum phase transfer function, non-minimum phase transfer function, all pass transfer function. So, what is this classification? How this classification has come? So, the classification of the transfer function minimum phase, non-minimum phase and all pass transfer function depends on the location of poles and zeros in the system or in the transfer function. Now, what is a minimum phase? If all the poles and zeros of the transfer function lies in the left half of the S-plane, then we say the transfer function is minimum phase transfer function. So when you look at the poles and zeros, we need to look at only finite poles and zeros. Infinite poles or infinite zeros are always at origin. So not origin poles, the other poles which are finite, and those poles and also finite zeros, they must lie in the left half of the S-plane. Then we call the transfer function is minimum phase transfer function. The second classification in the classification is non-minimum phase transfer function. So in this case, if minimum or at least one pole or one zero lies in the right half of the S-plane. Generally we talk about the zeros. Whenever zeros are lying in the right half of the S-plane, we call it as non-minimum phase transfer function. So we know that whenever the pole is in the right half of the S-plane, the system is unstable system. But when zero is the right half of the S-plane, the system is not unstable, but still we call it as non-minimum phase transfer function, and its behavior is completely different from the minimum phase transfer function. Now, so I am going to take one example for these two before going to explain about the all pass transfer function. For minimum phase, g of s is equal to s plus 1 divided by s plus 2 into s plus 3. So there is one zero and there are two poles. When you locate poles and zeros in S-plane, now I have one zero here and one pole and another pole, minus 1, minus 2, minus 3. Therefore, all these three finite poles and zeros in the left half of the S-plane, so that particular g of s is the minimum phase transfer function. Now, so out of this transfer function, I am taking one zero and placing the right of the S-plane, which means my transfer function results g of s is equal to s minus 1 on s plus 2, s plus 3. So in the numerator I have s minus 1, which means my 0 is now in the right half of the S-plane. So when 0 in the right half of the S-plane, poles in the left of the S-plane, and this transfer function is non-minimum phase transfer function. Sometimes even the pole in the right of the S-plane, zeros in the left of the S-plane, it is also behaves like non-minimum phase transfer function. In general, we call such a systems also non-minimum phase transfer function, but that system is unstable system. So what is all pass system? So in all pass system, whatever the zero that is available in the right of the S-plane, symmetrically there exists a pole in the left half of the S-plane. For example, I have transfer function g of s is s minus 1 upon s plus 1. So that is, I have one zero at s is equal to plus 1 and one pole in s is equal to minus 1. So when you look at here with respect to the imaginary, both are symmetrical each other. For every zero in the right of the S-plane, if there exists a pole in the left of the S-plane, that particular transfer function is called all pass transfer function. Then what is the use of the all pass transfer function? Now, so I have a non-minimum phase transfer function which obviously behaves differently when compared with the minimum phase transfer function. So one example which I have taken, 1 0 in the right of the S-plane, s is equal to plus 1 right side, and I have two poles, s is equal to minus 2, s is equal to minus 3. So I want to convert this non-minimum phase transfer function into minimum phase transfer function. So if you want to do that, then exactly I can place one all pass transfer function. So at right hand side I can place s is equal to one pole in the right of the S-plane, s is equal to plus 1, and 1 0 in the left of the S-plane, s is equal to minus 1. So in this case I can cancel poles and zeros which are there in the right of the S-plane. Theoretically we say we cancel poles and zeros there, but practically it is not possible. The effect of the pole at s is equal to plus 1, effect of 0 s is equal to plus 1 still exists. Theoretically we can cancel them, and this non-minimum phase transfer function can be modified into minimum phase transfer function. So in general we can return MPS, that is minimum phase transfer function, is equal to non-minimum phase transfer function multiplied with the all pass transfer function APS. That is what the advantage of your all pass transfer function.